Hey guys, Miss Marusik here, and in this video we're going to look at calculating using the combined gas law. This formula is on our formula chart, P1V1 over N1T1 equals P2V2 over N2T2. Anytime you're using either 3 or 4 of these variables, we would call it the combined gas law. But keep in mind that sometimes some of these variables remain constant. So if you're only using 2 of the 4 variables, if only 2 of them are changing, then that means you could be just using Boyle's law, Charles's law, Gay-Lussac's law, or even Avogadro's law. So all of those other laws, their formulas are hiding in this one. We can just cross off things that remain constant in the problem. Now there is a worked example on here for you. So if you kind of want to look through it, you're more than welcome to. I'm just going to jump into one today, just so that way we can talk through it and see exactly how it works. So looking at the next example here, it says that we have a 5.20 liter sample of gas heated from 25 degrees Celsius to 100 degrees Celsius. What is its volume in liters at the higher temperature if the pressure and the amount remains constant? The first thing I'm going to do is I'm going to go look for any kind of numbers they give us in the problem, and also for a how much, what is, how many kind of statement. What exactly am I trying to solve here? So the first number I see is 5.20 liters. I recognize liters as being a volume. I see my next variable here is 25 degrees Celsius. I recognize that as being a temperature. I see another temperature here of 100 degrees Celsius. And I'm looking for what is its volume in liters. So I see here that I have multiples of different variables. I have 2 temperatures and 2 volumes. And so what I need to do is I need to set one set of conditions as the 1 or the initial values, and then the other values as the 2 or the second set of conditions. I notice here that the volume that we're looking for is at the higher temperature. So what that means is that this higher temperature needs to go along with that volume. So I'm going to call that T2 and V2, whereas this volume and this temperature that go together, I'm going to call that V1 and T1. So you're going to have to kind of pay careful attention as to which variables go together. I do notice that both pressure and amount remain constant, so I don't need to write down those givens. It's not necessary here. So the next thing I want to do is I want to check my units. And when you're checking your units, you want to look for kind of 2 specific things. First off, you want to make sure any volumes and pressures are in the same units. It doesn't matter for combined what those units are, they just need to be in the same. So for example here, my volumes are both in liters, so I don't need to convert one to match the other one. Those already match. Now for temperature, I do need to be aware of the units. Remember, for these proportions to hold true, I need a temperature scale that has no negative numbers. So these temperatures must be in Kelvin, and I notice here that neither one of them are. Now if you forget what the conversion is, don't worry. On your formula chart, it does have that Kelvin equals degrees Celsius plus 273. So I just need to add 273 to both of these. And when I do so, 25 plus 273 will be 298 Kelvin. 100 plus 273 would be 373 Kelvin. All right, so I've got everything in correct units. I next want to write my equation. Now, if you can kind of already see what remains constant, you don't have to write all of the variables. But a lot of times I like to go ahead and write down the whole combined formula. Anytime I see I have 2 volumes or 2 temperatures or 2 pressures, I know I'm going to be using my combined equation. And as a reminder, this is on your formula chart. So, you know, if you have a moment in the middle of a quiz or a test where you're like, oh, I don't remember that formula, good news, it is on our behavior of gases section. So you can see it right there. There's our combined formula. Now, we don't need all of these variables for this problem. Again, pressure and amount remained constant. So what that means is that I can cross off pressure and amount out of this equation. Now, if you knew that those remained constant before you wrote the equation, you could have just wrote V1 over T1 equals V2 over T2 here. You don't have to show those other two things canceling out. By the way, if a variable is not mentioned in the problem, like even if they hadn't told us that pressure and amount remained constant, if it's not mentioned, then we can assume that it does remain constant. Usually they only mention things that actually change. So if a variable wasn't mentioned, assume it stayed constant. All right, next I'm just plugging in my numbers here to try and get myself an answer. So my V1 was 5.20. My T1 was 298. My V2 is what I'm looking for. Now, if it makes you feel better about algebra, write X there, right? Same thing. And then my T2 was 373 Kelvin. And now I just want to solve. I, on these, usually like to cross multiply. Obviously here you don't have to. You could do this math here, the 5.20 divided by 298, and then I can see to undo divided by 373. To bring that to the other side, I would multiply. The only reason I sometimes encourage people to cross multiply is when your unknown variable is in the denominator, it's a lot of times a lot easier to see how to solve it if you do cross multiplying. So totally your choice on how you solve that algebra. Honestly, as long as you're getting a correct answer in solving your algebra, you're going to be in good shape. So what I'm going to do is I'm going to cross multiply here. I would have had my 5.20 times my 373. That would have equaled V2 times the 298. So then to bring the 298 over, I would divide by it. And that gets me 6.5087, yada, yada, yada. Now, obviously, I don't want to include all those digits. It's not necessary. So I go back and I look at all of my original numbers, and I notice that all of my original numbers only had 3 significant figures. And so therefore, I'm going to include 3 significant figures in my answer here. Now, when I cut this off, that 8 would round up to 0. So that leaves me with my V2 equaling 6.51. And if I go back and think about my unit, remember we were trying to solve that in liters. All right, now as far as whose law, this is where it's really helpful to remember those sayings of Charles watches TV, Gay-Lussac uses toilet paper, Boyle is vice president. I know they sound really silly, but it's a great way to kind of remember who had which law. If I'm thinking about manipulating T and V, who watched TV? Again, that's our friend Charles. Now, if I use more than 2 variables, even if it's just 3, it doesn't have to be all 4, but even if I use 3, I would call it combined. But if I only use 2 variables, then we want to give it that name of either Boyle's, Charles, Gay-Lussac's, or Avogadro's. Okay, let's do another one together. So go ahead and flip to the next page. All right, so here on example 9, I'm going to go through it again and kind of notate exactly what my variables are here. So starting off, I have a 3.50 cubic foot, and that's the same thing as writing feet cubed. So that would be a volume. Sample of nitrogen whose pressure is 79.1 kPa. Now I see these kind of go together, so I'm going to go ahead and call these V1 and P1. Now it tells us that this is going to expand to 6.10 cubic feet. So that means my V2 is going to be 6.10 feet cubed. While the pressure also changes, so I'm going to change that to P2 to 680 torr. Now, it says at the expanded volume, the temperature of the gas is found to be 28 degrees Celsius. Well, let's look here. I've got 3.50 feet cubed and 6.10 feet cubed. The expanded volume would be our bigger volume. So that means that this second set of conditions, our T2 is going to be 28 degrees Celsius. And it wants to know what was the original temperature in Celsius. Now, there is a lot going on with checking units here, so we got to be real careful. So first off, I would want to check our volumes and pressures in the same unit. Well, both our V1 and our V2 are in feet cubed, so that's good to go, right? All right, but then I look at my pressures and I'm like, ooh, those are not in the same unit. One's in kPa and one's in torr. Now, this is where you kind of get to pick what unit you want to use. We either need to get these both into kPa, or we need to get these both into torr. I wouldn't take it into some other unit because then you have to convert both of them. I would just take one into the same unit as another one. I'm going to put both of these into torr, but again, it really doesn't matter. As a reminder, under constants and conversions, you have some pressure equalities here that can help you set up a one-step dimensional analysis in order to convert your pressure. So again, this is only going to take one step to convert your pressure. So again, I'm going to convert the 79.1 kPa and as I said, this is just going to take one step to make this conversion. If kPa is on top, then I want to put kPa on the bottom, and I'm going to take this into torr to make them match up. So then here's where I go to my equality and look what numbers go with those units. So 760 was with torr, 101.33 was with kPa. So I just plug those in where appropriate. 760 with torr, 101.33 with kPa. And I'm going to enter that into my calculator and get myself an answer here for that portion. So 79.1, open parentheses, 760 divided by 101.33. And I see that gets 593.2695, yada, yada, yada. Now, here's the deal. We're technically not done with the math yet. So if you wanted to use that whole number, you could. But you could go ahead and round for sig figs already. So I would probably just use 593 here. Torr. And again, what we did is we are converting that kPa into this torr value. So this is going to end up being my new P1 instead of the 79.1 kPa. Now, we've checked to make sure volume and pressure are in the same units. All right. So we went through all of that. But remember, the other thing I need to check is that temperature is in Kelvin. Now, this is where I always get lots of questions. People say, well, but Miss Marusik, this says degrees Celsius, so wouldn't I want to do this problem in degrees Celsius? Nope. And I'm going to tell you why. Your proportions that we set up with that combine are only true if that temperature is in Kelvin. So even though it wants the answer in degrees Celsius, we are going to have to figure out the answer in Kelvin and then convert it back to degrees Celsius. That proportion has to be set up in Kelvin, which means I've got to convert this to Kelvin as well. When I add my 28 plus my 273, that's going to get us 301. And so I'm going to end up with getting an answer that I will then have to convert. So we're going to have to be really careful here. So keep in mind, even if it wants the answer in Celsius, you must convert into Kelvin. You have to do the problem in Kelvin. I can't stress that enough. Be very careful on that. I see people mess that up all the time and then get the wrong answer and they're like, but I did it right. And I'm like, no, you didn't. So just be really careful. All right, so now let's write our equation. I see I have two sets of conditions of everything. So I know I'm using our combined P1, V1 over N1 T1 equals P2 V2 over N2 T2. Now, I noticed that they mention things about volume and pressures and temperatures, but nowhere in the problem did they mention anything about amount, nothing about moles. And so therefore, I can assume that that stayed constant and cross it out. All right. So now I'm going to plug in all of this. So again, since I've already checked my units, I'm not going to worry about putting units into my work here. But really what would happen is that all your units would end up canceling out. That was why we had to make them all match. So for my P1, be careful. We want to do our newly converted 593 torr. Our V1 that goes along with that is the 3.50. Our T1 is what we're looking for. If you don't want to write T1 there, you could write X if that makes you feel better about solving algebra. It really doesn't matter there. All right, so then on the other side, my P2, 680. My V2 was the 6.10 over my T2, which was 301. All right, so again, it doesn't really matter how you solve this algebra as long as you're getting a correct answer. I, again, like to cross multiply. So what that would mean is that I would end up multiplying these guys together, and that would equal these three multiplied together. So once I multiply these three, if that equals the other ones multiplied together, I can then divide those over. So I would multiply by 593 times my 3.50 times my 301, and that would equal, again, these multiplied together, but that means I would divide these two guys over. So I'm going to divide the 680, and I'm going to divide the 6.10. So again, there's other ways to solve this algebra. I like cross multiplying, but take your pick on how you feel most comfortable as long as you're getting a correct answer. And this is a really good one to check since that number that we're looking for is in the denominator. So if you want to try solving the algebra a different way, as long as you're getting the correct answer, you're going to be in good shape. So I got here that the T1 is equal, and I'm going to round this for sig figs. I notice all my numbers had 3 sig figs, so I'm going to round this to 151. But we got to be really careful here. This is a temperature that I got from solving this problem here with proportions. But remember, this is going to solve it in Kelvin. But what did they want that answer in? They wanted that answer in degrees Celsius. So we're going to have to convert this back. Well, how do we do that? Well, we would subtract our 273 from this. So when I take my answer, 151, and subtract the 273, that's going to get a negative 122 degrees Celsius. And so that would be our final answer there. Now, again, if you had tried to solve this proportion using Celsius instead of Kelvin, your answer would have been totally wrong, and you would have been totally sad. So be really careful there, okay? Now, as far as the law name, again, here I used more than just 2 variables. So I would have called this combined. All right, so here's the deal. There are 3 more problems here. What I'm going to let y'all do is see if you can work these problems and get yourself an answer. I'm going to talk about each of the problems in this video. So if you need to hear it explained, you're more than welcome to stick around for the rest of this video. But if you can solve these without me, then more power to you. Yay. As you can see, it's just simple algebra. And so most people usually feel pretty good with doing these types of problems. There are a couple quirks on a few of these, so I'll kind of talk about that before I show you each of the answers to them. So looking at the next example, example 10, you'll notice that they give us a problem here. So what I want you to do is to take a few moments. I want you to pause this video, and I want you to go through that same process that we did on the other problems. I want you to see if you can list your givens, check your units, see if, volumes and pressure in the same units, make sure your temperatures are in Kelvin, write your equation, cross off anything that either stayed constant or just wasn't mentioned at all. Plug in your numbers and see if you can get an answer. So I'm going to go ahead and give you all a moment to pause the video and try out this problem. So pause the video, go try it out. All right, did you pause it? Did you try it out? I hope you did. Woohoo! Let's see how we did. Let me scooch this up here. All right, so on this problem, it told you that a gas was found to have a pressure of 700 torr at a temperature of 54 degrees Celsius. And then it said if the volume of the gas under these conditions is 3.21 liters, what was the original volume in liters when the temperature was 20 degrees Celsius and the pressure was 700 torr? And some of you might have noticed as you were writing all this data that you were like, hey, wait a minute. The pressures stayed constant, like it was 700 torr for both. So since the pressure was constant, I didn't need to include that in your formula, in your work. Now, if you did, what you would have seen is they would have just canceled each other out. So you would have still gotten the same answer if you had included them. You just didn't need to. Now, on the temperatures, you did have to convert those Celsius into Kelvin. If you didn't do that, your answer would have came out incorrect. So then I just went down here to my equation. I crossed off pressure and the amount, the moles weren't even mentioned, so I assumed that that stayed constant as well. Plugged in my numbers, did some cross multiplying to solve V2, and that should have gotten a V2 of 2.88 liters. As far as the law is concerned, since only temperature and volume changed, that would have been Charles's law. All right, let's flip to the next page. There's a few more on there. All right, so here is number 11. I'll give you some time to read through this and see if you can solve it. So go ahead, pause the video, try it out, see if you can figure it out. All right, did you pause me? Did you try it out? I sure hope you did. Let's check it and see how we did. All right, so it told us that a gas expands from a volume of 17.3 centimeters cubed to 24.5 centimeters cubed. So those were my two volumes. At the expanded volume, so that would be this 24.5 because that's the bigger volume, the pressure was found to be 99.3 kPa. So I did want to make sure that that volume and pressure went together, so I assigned those the second set of conditions. By the way, a manometer is just a type of a piece of equipment we can use to record pressure. Manometers measure an experimental pressure inside of a container, whereas a barometer measures environmental atmospheric pressure. All right, so I wanted what was the original pressure of the gas before it expanded in millimeters of mercury if temperature and amount are constant. So here's the deal, checking my units. My two volumes matched up. Awesome. I didn't have temperature at all, so I didn't have to worry about making sure I was in Kelvin, but I needed those pressures to match up. Now, since it wanted the answer in millimeters of mercury, I went ahead and converted my kPa into millimeters of mercury. Obviously, you could do that conversion at the end, and you should get roughly about the same answer regardless of where you end up converting it. Okay? So when I set up this problem, I then said, hey, amount and temperature remain constant, so I canceled those out. So then what I did is I just plugged in my numbers. P1 is my unknown with the 17.3 for the V1. 745 and 24.5 would be the second set of conditions. Now, when I solved this, I got 1055 millimeters of mercury, which if I rounded it to 3 sig figs, that would be reported as 1060. If you notice up above, the answer that they gave was 1050 millimeters of mercury. That sometimes is dependent on where you make your pressure conversion. Do you make it at the beginning or at the end? And sometimes that can ever so slightly adjust that number. So keep that in mind if you are doing some conversions in your problem and you get an answer that's a little bit different than a posted answer, like say, for example, on the practice worksheets, you're doing a problem and your answer is just a little hair off. Don't panic. This is a great example of not panicking. You are allowed some leeway, especially on these where you're having to do some sort of conversion, because it really does depend sometimes if you do that conversion at the beginning or at the end, or also how many sig figs you're keeping from that conversion. This would be Boyle's law, because remember, Boyle is vice president. See, the little sayings help. I know they're silly, but they work. All right, you've got one last one down here. Now, I am going to give you a little hint on this problem. My hint is that it says conditions were changed to STP. When they tell you that you're having STP conditions, that is telling you a set of numbers without literally telling you what the numbers are. So keep in mind that you may want to glance at your formula chart to see if you can figure out what STP conditions would be. All right, so with that said, go ahead, pause the video, and see if you can try this out. All right, did you pause it? Did you try it out? I hope you did. All right, last one. All right, so I listed my givens. So it told us that the volume was originally 8.90 liters at 100 degrees Celsius and 113 kPa. But then it said that we're going to change this to STP conditions, and we want to know that new volume in liters. So my V2 would be question mark liters. My STP conditions, if you looked at your formula chart, is 0 degrees Celsius and 1 atmosphere of pressure. Now, I did have to check my units. Volumes already matched up, so that was good. Now, the pressures didn't match up, but here that would be an easy fix, because we know from the pressure equalities that 1 atmosphere is 101.33 kPa. So I didn't even have to do a dimensional analysis here to go ahead and convert that. This was much easier. I did have to convert both of my temperatures from Celsius into Kelvin, so I added my 273 to both of those. And so then I just plugged into my equation. I did not have the number of moles mentioned anywhere in the problem, so we assumed that those did stay constant. And so when I plugged in, here are my number setups, and I wanted to solve for V2. So I did some cross multiplying, and that solved V2 being 7.26 liters, again using 3 significant figures. If you notice, all the problems that we've done used 3 sig figs, and we tried to keep that pretty consistent in this unit, both on the notes as well as on your practice, in your quiz, in your test. If you use 3 significant figures on all your problems, you should be in pretty good shape. Since we used more than just 2 variables, we would call this combined for the law name. Even though we didn't use all 4, we still used more than 2. So combined is the appropriate name to put here. All right, I hope you're feeling good on some of this algebra and setting up these gas law problems. My advice to you is to practice with these. The more you practice with this math, the more confident and the faster that you get with it. That's one thing we want to do, is build up our efficiency with these problems, okay? All right, if you have any questions or need any help, please feel free to email me. Bye, guys.